In this example, what we're going to do is we are going to use Ampere's law to prove that the strength of a magnetic field inside an ideal solenoid is mu naught times n times I. Now, in the lecture slides, you are given this relationship that this is the strength of a magnetic field in a solenoid, but it could be very instructive for the goal of understanding what Ampere's law is and really get a feel for Ampere's law to work through this derivation. So we are assuming that we have an ideal solenoid. In the case where our solenoid is ideal, the magnetic field is going to be zero outside the solenoid. Now, a solenoid is just a coil of wires wrapped in the shape of a cylinder. So on the board over here, we are basically looking at a cross section of our coil. So here's my coil, and then we are looking at a slice through the center of the coil of wires. So the current is wrapping around in a cylinder, and on the board is drawn right down the center. Now, the way this is drawn, I have circles with X's in it to indicate up there the current is flowing into the board, and I have circles with a dot down here to indicate current is flowing out of the board. So current is flowing out of the board, it is turning up and flowing into the board above. And then behind the board, it's going to flow down and out. So the current is flowing in a cylindrical fashion, kind of like this. Okay, so in the case of an ideal solenoid, we want to ask what is the direction of the magnetic field. So the magnetic field will point along the central axis of the solenoid. So in this case, the magnetic field will point either to the left or to the right. So to find the direction of a magnetic field, I could use the right-hand rule where I have my four fingers as the curly part and my thumb as the straight part. Now, if I know that the current is flowing into the board up top and out of the board down below, so if I curl my four fingers into the board above and then out of the board below, when my four fingers are above my thumb and into the board, my thumb points to the left. When my four fingers are below my thumb and coming out of the board, my thumb points to the left. So the direction of the magnetic field inside the solenoid is pointing to the left, like so. Okay, so we use the right-hand rule because we know current flows into the board up here, out of the board down there. We found the magnetic field is pointing to the left. So, what is going to be the strength of the magnetic field? How are we going to arrive at that result? To do that, we're going to need to use Ampere's law. So, Ampere's law is a statement where we have this term, sum B parallel delta L is equal to mu naught I enclosed. And this assumes we walk around a closed loop. Now, the way this equation is just written, it doesn't really give us a feel for what we are looking at. Okay, if I walk in a closed loop, I could picture that. I have to come back to my starting point. B parallel is just how much of the magnetic field, if there is any, is in the same direction as the step I take, where the step size is delta L. I could imagine walking around some wires, so maybe some wires are coming or going, and that would be my I enclosed. When we work with Ampere's law, the shape of the path we walk is important. And just like with, for example, Gauss's law, the shape of what we choose could have a big effect. So a very convenient path for a path we're going to walk will be something like this. So I will draw a path that begins right at the surface of the solenoid. I will walk straight upward, and then I will turn and walk to the right, and then I will turn and walk straight downward, and I'm going to walk between the wires and walk down even more. Somewhere inside the solenoid, I'll turn and start moving to the left. And then I am going to walk, turn and walk straight up, and I came back to my starting point. So I am going to choose this to be my closed loop. So, okay, I have a notion of a closed loop. Let's see, what do we want to do? I'm going to begin by considering Ampere's law. I'll just look at the left-hand side of Ampere's law for the moment. We'll get some results here, and then we'll think about what does the right-hand side of Ampere's law say. So, around a closed loop, to make my life easier, I'm going to label different sections of the closed loop. So I'll say part one of this closed loop, or part one of my journey in a closed loop, will just be when I'm outside the solenoid, walking straight upward. Part two of my journey will be when I am walking to the right. Part three of my journey will be when I am walking downward, but I'm still outside the solenoid. Part four of my journey will be when I'm walking down, but inside the solenoid. Part five of my journey will be when I'm walking to the left. And part six of my journey will be when I'm inside the solenoid and walking up, just before I get back to my starting point. So, I am just labeling different sections of my closed loop. Part 1, 2, and 3 are all taking place when I'm outside the solenoid and walking either up to the right or down, respectively. Part 4, 5, and 6 of my journey around a closed loop take place when I'm inside the solenoid and I'm walking down to the left and upward, respectively. So, the entire closed loop I divided into 6 parts. So I'm going to write out this sum as 6 terms in total. And at first 6 terms, that seems like a lot of work, but we're going to eventually see that it will get nicer very quickly. So the full closed loop is divided into 6 parts. So I could say the entire closed loop, so the sum of B parallel delta L is equal to B parallel delta L for part 1 plus B parallel delta L for part 2 plus B parallel delta L for part 3 plus B parallel delta L for part 4 plus B parallel delta L for part 5 plus B parallel delta L for part 6. So this is the part of my closed loop that is section 1, 2, and 3. So this is section 1, 2, and 3 of my path. I just don't feel like labeling them with more subscripts 1, 2, and 3. So this part right here that I'm designating is when I begin and walk straight up. And then for part 1, turn and walk to the right. For part 2, turn and walk downward for part 3. Now, anytime I'm outside the solenoid, the strength of the magnetic field is 0. We are beginning with that assumption. It can be proven. The actual proof is beyond the scope of this course, so we're not going to worry about that. But in each of these sections, there is no magnetic field. So the magnetic field parallel to my steps are going to be 0 for each of these. So B parallel here will be for 1, 2, and 3 are going to be 0. So right away, I got rid of 3 terms very quickly. If I look at my other parts of my path, I have B parallel times the direction times my step for section 4. So now what I have is the sum of B parallel delta L around a closed loop is equal to 0 plus 0 plus 0 plus B parallel delta L for section 4 of my path plus B parallel delta L for section 5 of my path plus B parallel delta L for section 6 of my path. Now, if I look at section 4 and section 6, I notice that the magnetic field always points to the left, and my path is either straight down or straight up. In both of these cases, for 4 and 6, my path is always going to be perpendicular to the direction of the magnetic field. And so there is no component of the magnetic field in the same direction as my step. And because of that, because the magnetic field is perpendicular to section 4 and section 6, this B parallel term is again going to be 0. The magnetic field is non-zero inside the solenoid, but the magnetic field is pointing perpendicular to the direction I am walking. So this B parallel, well, there's nothing parallel to my step. So these two terms are also going to be 0. And the reason for this is B is perpendicular to the direction of steps 4 and 6. So right away, the entire left-hand side of Ampere's law is just equal to B parallel delta L for section 5. So the only term that is going to actually contribute to Ampere's law is this step right here. The part of the step that is in the same direction as the magnetic field and inside the solenoid. So what is that going to be? Well, the magnetic field has the same strength everywhere in the solenoid because we're assuming the ideal case. So I could just write that as, and the magnetic field is entirely in the same direction as my step. So I could write that as being equal to B times delta L, where this B is going to be the full strength of the magnetic field. So full strength of magnetic field inside the solenoid. Magnetic field inside the solenoid. Okay, we talked about the strength of the magnetic field inside the solenoid, and we looked a lot at the left-hand side of Ampere's law. Let's look at the right-hand side of Ampere's law. So the right-hand side of Ampere's law is mu naught I enclosed. So I have, for the left-hand side, 0 plus 0 plus 0 plus 0 plus B delta L plus 0 equals mu naught I enclosed. Mu naught is just a constant of nature, so I'm just going to keep it around. I don't really need to think about it. It's just, and wherever it ends up, it ends up. I enclosed, how much current did I walk through? Well, I didn't walk over one wire. I walked over 1, 2, 3, 4. I walked over some number of wires greater than 1. So I could say from here to here, my closed loop encircled some number of wires. Encircled some number of wires. And in principle, I could go ahead and count how many wires I think I encircled. So let's suppose I encircle, I don't know, let's suppose I encircle X number of wires. So I walked around X wires. Okay, well then, so what we could do is this B delta L term just becomes the total strength of the magnetic field inside the solenoid times the size of the width of the path we are walking, how far in the left-right direction we walked. On the other side, mu naught is just a constant of nature. I'm going to keep it around. And I enclosed being how much current I walked around. I could say this is just the current in one wire times X, where X is however many wires I walked around. Now, it might look somewhat arbitrary. B delta L over mu naught I. Okay, I could write that as B is equal to mu naught times X over delta L times I. Okay, the current flowing through the solenoid, that's my I. The mu naught, that's a constant of nature. What about this X over L? Well, if I take a really wide path, a really large delta L, I'm going to walk around a lot of wires. Or if I take a really narrow path, I'm only going to walk around a few wires. So even though each of these terms individually could be large or small, in other words, both of these terms individually are arbitrary, the ratio of them, a big number over a big number or a small number over a small number, that ratio is just going to be the number of wires in the solenoid divided by the length of the solenoid. So as long as the wires are packed evenly throughout the solenoid, as long as the wires are evenly spread throughout the solenoid, which is an assumption we are going with, are evenly distributed along the solenoid, I could just say that X over delta L will be the same thing as total number of wires divided by total length of the solenoid. I could say X over delta L could be written as capital N over cursive L, where capital N is the total number of wires, cursive L is the total length of the solenoid. So this is the total number of wires. Or loops in the solenoid, and this is the total length of the solenoid. So if I want, I could then write the strength of the magnetic field is equal to mu naught capital N over L times I. Now sometimes if I think total number of wires divided by total length, I could kind of think of that as a density of wires, how densely the wires are packed together. So if I write or define a new quantity as little n is defined to be big N over L, so this is equal to the number of, so little n is the number of wires per unit length. Unit length is basically The unit of distance in SI is 1 meter. So how many wires would we have if our solenoid were 1 meter? That's basically going to be little n. Or we could have the total number of wires divided by the total length, and then we could have a solenoid of 10 centimeters long or something other than 1 meter. I could also write the strength of the magnetic field inside a solenoid as B is equal to mu naught times little n times I. And both of these equations are perfectly valid. I feel more often you see this one up here, but this one is fairly common too. So they're both worth knowing. And basically I'll say, be careful if you have n. Be cognizant of, are you working with a big N or a little n? And that depends on the context of the problem you're looking at.